this lecture is going to be about the relation between the parameters of the tree and the stocks. What is it? What is this, and what's the aim of this lecture? Maybe you remember the rule how we construct the binomial tree. We should know the initial value, and you should know the parameters u and d. But how we can find these parameters if we have the statistics about stock prices? And this lecture maybe give the answer of these questions. So let T capital represent the duration of the contract in years, and N capital is number of equal periods between trading dates. So you see that this period from 0 to T capital, and if we have N periods, this N capital, so the duration, the length of this period will be dt. Yes, will be dt. And we can find this dt as t divided by n. And let R capital denote the continuously compounding annualized interest rate. It is not 1 plus R little as a previous lecture. It is only interesting rate. But R little is interest rate for one period. So if we know this R capital, so for one period it will be R multiplied dt, or multiplied T capital and divided by n. And you remember how we can extend the exponential to this series. It will be 1 plus x squared divided by 2 plus x cubed divided by 3, and so on. If we if we replace instead x r capital dt, and we leave only linear part, it will be 1 plus r capital dt, but r capital dt it's r little, so it will be 1 plus r. And from this we can find r little, and it is interest rate for one period, and it will be e exponent to the power r capital dt minus 1. It's very useful formulas for us. And now we mentioned that you remember that it is a necessary and efficient condition 1 plus more than d and less than u, and it is condition for existence of risk neutral measure. Yes, and if it's not random, not stochastic, and d equals u, so d and u will be equals only 1 plus r, or exponent to the power r dt. You remember from this slide. It is the first notation. And second notation, it is, you remember the formula for continuous compounding rating. And from this, we can find R, and it will be log returns. Log returns. You remember it is, if I'm not mistaken, the second lecture, a short excursion into finance. But what we would like, we would like to research the similar value, but if we take not BT, where BT will be deposit. But if we would like to take stock price and to research uh, log returns for stock price, and we would like to find mathematical expectation and variance. What is solving this problem? You know this rule for building the binomial tree, that the next price equals the previous price multiplied by the factor O if the price goes up, or D if the price goes down. And I can write a logarithm of this fraction as sum of logarithm. Do you agree with this? Can what is about this equivalence? Really, we can check this. If n equals 1, it will be log s1 log s1 divided by s0, so log s1 minus log s0. Next, for n equals 2, it will be log s2 minus log s1. And so on. And for n equals n capital, it will be log s n capital minus log s m minus 1. Yes, and you see that we have log s1 with plus, log s1 with minus, log s2 with plus, and log s2 with minus. And after this operation, we have only this and this, and it will be log Sn divided S0, and it's very useful for us. And the third, the increments are independent. So it's our assumption or notation. Oh, sorry, I would like clear. And after that, we can solve our problem to find the expected growth rate. we would like to find mathematical expectation of this y, but this y capital we can write as sum. We showed this, just showed on the previous slides, and mathematical expectation of the sum is the sum of mathematical expectation. Do you agree? And after that, we should find the mathematical expectation of this value. But you know that the rule how we can get the next value as n if we now at the value as n minus 1. It is the mathematical expectation. It is the Sn multiplied Qu and or as Sn minus 1 multiplied d and multiplied Qd. But it is full logarithm. So you see that Sn minus 1 crossed, and we have this ln u Qu plus ln d Qd, and it is for every term, but the number of this term, the amount of this term is n, so we should multiply it for n. Maybe I see mistake on this slide, because Qu it is not under logarithm, it is maybe after backwards. Do you understand how we can find the expected growth rate? Is it clear, Danilo?
Oh yeah, it looks good.
You know what is mathematical expectation, yes? It is this, what is mathematical expectation? It is Sn, it is random value, and it will be or Sn minus 1 multiplied U, or Sn minus 1 multiplied multiplied D, yes? This Sn, this Sn, it is Sn minus 1 multiplies U with probability Qu OS n minus 1 multiplied d. So if we find mathematical expectation, and there are two cases, yes, two cases and two probabilities, and we replace this as n minus 1 multiplied u and as n minus 1 crossed, and we have only ln u multiplied Qu, and in the up in the down scenario we have only ln d multiplied Qd. Can I go on? Danilo.
Yeah.
Yes, thank you. After that, we should find variance. It is very similar. We know that the variance, the expression multiplied constant, and constant we can write in square before variance, yes? And after that, variance sum equals sum of variance, because we assumed that this value are independent. And for every n, it is the equals terms. So we compute only for any n and multiply it by n capital. And how we can then find variance of this? As it is, as I explained in the previous slide, for computing variance, it is the value square multiplied probability minus minus mathematical expectation square. But if we find the value square multiplied probabilities, we are thinking in the same way. So there are only two value for random variable Sn. It is Sn minus 1 multiplied U, or Sn minus 1 multiplied D. And in both cases, n minus 1 crossed, so we have only ln u square multiplied qu and ln d square multiplied qd, and minus this mathematical expectation, it is from this slide, square. And after that, if we find the square of this sum, it will be ln square u and qu square minus d square and minus minus the double product of this value. And you see that this will be ln u square and qu square. And if we write this before bracket, it will be qu, but this, it will be 1 minus qu, it will be qd. So we have this expression, and it will be written as ln u divided by d square, qu qd. So we found the mathematical expectation and the variance of these logarithms. And there are interesting statement about the expected returns of the stock. We can find the annualized expected return. It will be v divided as n as 0 minus this 1, and as n divided by a 0, we can written as a product of this expression. And mathematical expectation of each Sn divided by Sn minus 1, it will be equivalent. So we can write this as to the power n. And so it is similar as previous slide. We know that Sn a random value, and we can write this as S minus 1 multiplied U or Sn minus 1 multiplied D, and find mathematical expectation over this. After that, you know that this expression, it's 1 plus R, it's 1 plus R. UQ plus DQD, it's 1 plus R. You know this. And we can, from the first slide, we can replace this by this expression. And finally, we have that it will be the analyzed expected return is 1 divided by T, ERT minus 1. So we can formulate the theorem that under the risk neutral probability measure induced by the binomial tree model, the expected return of the stock is identical that of riskless bond. And the third part of this lecture, it is our aim, implementation of binomial trees. So we've found the mathematical expectation, and we found variance, yes, for log returns. But we can find for log returns from real historical data. We can find mu and sigma square. For example, we have historical data S0, S1, S2, and S100. No. And S100. We can find this log returns. It is log S1 divided by S0 log S2 divided by S1, and so on. And we can denote, for example, this U series as H1 OH, H2, and so on, and H100. And for this series, we can find average, and it will be mu. And we can find variance, and it will be sigma square. And we can substitute in this system. It is a real value from real historical data, and we can shoot over this system. But this system has two equations, but more unknown variables. So for solving this, we can use one of two methods, or method of symmetric probabilities, or method of symmetric limits. If we do assumption that QU equals QD and equals 1 divided by 2, we can easily shoot this system, and the solution will be the next. Or we can to apply this assumption that d equals 1 divided by u, symmetric limits. So u and d will be as follows. Mm. So, that's the main result of today's lecture. And maybe that's all for today. And on the next lecture, we will show how to find the formula for a fair price for continuous binomial tree.
I'm sorry, I have a question.
Do you have a question? Yes.
Yeah, I have one. The question is, can you come back to the previous presentation and to the situation with the dice?
Can. Yes.
Please, if you.
Just a moment.
Yeah. Yes, this one. And actually, I didn't get why we write at the beginning of the left part of the equation 4 plus 5 plus 6. Why these numbers? Why not 3 plus 4 plus 5 plus 6? That's the question.
The question about this
Yes.
expression. Yes. This step, it is step after this. Now I'm going to explain. You understand how we can find 3.5? Yes.
Yes, but
it's mathematical expectation if we throw die only once and we can win. Yes.
Okay, and why it is 3 and 5? Why it is not real?
3 and 5, it is mathematical expectation. Just a moment.
Okay, I got that.
Yes.
So you mean 1 divided by 6 multiplied by 1 plus 1 divided by 6 multiplied by 2, yes?
Yes, and so on. And yes, and it is 3.5. And now let us imagine that we can possibility to through only 2 times, and the final time, the mathematical expectation we have already computed is 3.5. But now we threw this die and we think that if you see on the die 1, 2, and 3, our decision is to continue a game. Understand?
I understand this, but I don't understand how it is connected with this equation.
So I can explain. If we continue the game, so the mathematical expectation will be 3.5. but we continue game in the case if you see one on the die, two on the die, and three on the die. In this situation, we continue the game, but this situation is taken with probability 1 divided by 6. But in this situation, we get not 1, 2, and 3 because we continue. But if we continue, the mathematical expectation, the next step will be 3.5. Understand?
Uh-huh.
But situation 4, 5, and 6 with probability this, we not wait. So it is only this value. We can win only this value 4, 5, and 6. We say stop game, and for example, you see for stop game, so our win 4, stop game, our win 5, stop game, our win 6. But if you see 1, it is not stop game. We go on and we throw die again, but the mathematical expectation is 3.5.
Okay. And
Yes.
if we throw the dice, for example, 5 times. Here in this example, we throw the
Yes.
dice 3 times.
Every time we should compute this value, and our decision it is the number on the die less, we go on our game. But if more, we stop.
But if we have to throw the dice 5 times, do we have to
But
change this equation or not?
If we throw 5 times, we can compute for 3 throws, for 4 throws. It is process for computing. I cannot say final results because we should compute this.
And how? I don't understand. So this equation shows that second row.
Yes, this equation, this for second row. But from no, if we have a possibility to throw only 2 times, but for 3 times, I explained on the no before. So that's on. Now we have break, and after that we have practice lesson. Yes. So see you later.